Okay, so it is 1900, and it's been 1900, I know. It's been 1900 once before, and that was quantum mechanics. And I think what happened there was that they couldn't explain black body radiation, and I know, you got it, well, you know. You know, okay. Yeah, that's okay. They know we're not normal. You know. But there was black body radiation. They couldn't explain black body radiation. Planck basically sold his soul to the devil and came up with a quantum theory that they never could get rid of, right? And that became, as far as we know, the truth, right? And at about the same time, Maxwell had predicted, if you remember, mu naught is a magnetic formula, a magnetic constant, yes? When we're going to calculate magnetic fields and stuff like that, I believe we use that, or maybe we don't. Did we not use that? Yeah, we didn't use that, but that's okay. This is a magnetic constant. Epsilon naught is actually the K that we use for Boltzmann constant. It's really 1 over 4 pi epsilon naught. So when you get to like grown-up physics, you'll be using that. And the speed of light, as it turns out, okay, is 1 over the square root of those two constants multiplied together. And at that point, a shaft of light shone down from the sky. Trumpets played, you know, right? I mean, it was this epiphanal moment, right? That the speed of light is just some sort of simple thing. There's no other fudge factor like that. And that's because light, of course, is a electromagnetic wave. Yes? Okay. Now, here was the problem that they were wondering about, right? And the question was, if light is an electromagnetic wave, what's waving? It's kind of a little bit like the Winnie the Pooh, right? If no one's home, they go to Rabbit's hole and they say, "Are you home?" And Rabbit says, "No, nobody's home." Right? You know, if there's no one home, then who just said nobody's home, right? They figured this out, right? So if it's a wave, what is it a wave of? Sound is a wave of air. Air is compressing and rarefying, yes? Okay. Earthquake waves are waves of the crust, okay? And so light is a wave of, well, I don't know. What could there be? We know that light travels between the Earth and the Sun, and the Earth moves 19 miles a second, so it's reckoned, around the Sun. Yeah? So whatever it is that light is traveling through to get to the Earth has got to be fairly ethereal, yes? I'm working up to it here. It's not actually a joke, but this is where the word came from, right? It has to be a fairly ethereal substance. It has to be able to pass, solid stuff has to pass through it, right? In fact, we know light travels through glass, so whatever it is, right, has to permeate the glass, right? So they came up with this notion that light traveled through this stuff called luminiferous ether. Yes? This is an old theory. We don't believe this anymore. We now know that light can just travel through space. It can travel through nothing, which is a little bit crazy, right? Now, the next thing to do, and this is a curious thing, right, is to look at the Earth, right? The Earth is traveling around and around. Around and around goes the Earth, right? Okay, so here's the Earth. Oh, that's a fairly good circle. Okay. And here's the Sun, which is the source of all our power, right? And here is the Earth in let's see, I believe we're going clockwise, right, right? Okay. Here the Earth is in January, right? And here we are in Junuary, right? As we call it in Oregon, yes? January is that month that feels like January, but it's really June, and you think, yeah, there we go, right? So if the ether, if we're moving through the ether, we can't be at rest with the ether here and here, can we? Yeah? There's got to be at some point in the Earth's motion around the sun, we've got to move through the ether, yes? So if ether does exist, we ought to be able to detect it, yes? Yes. So what they did was they set up an interferometer. This is the Michelson-Morley interferometer. Now these things exist today. They are marvelously, spectacularly sensitive instruments. Okay, let me explain how it works, and then I'll tell you how sensitive it is, right? when we set it up, I don't know what they use. It has to be monochromatic light. It has to be all one color, right? We used a laser in college. They've shown a laser here. This is a half-silvered mirror. Half-silvered mirrors let half the light through, and half of it is reflected, right? You've seen these, like that mirror behind Nina is half silver. It looks like a mirror, but if you walk around the other side, you can see through it. That's what it's there for. If I ever need to spy on the room, Actually, I was going to put a television behind that, so when you turn the television on, right, you could see it miraculously, right? They have those, like people have televisions in their shower for that purpose, right? You turn the television on, you can see it, right? But if it's darker behind there, you can't see in there, right? Okay, so this source, half the light hits this mirror and comes back, and then, by the way, half of that light hits the source again, right? But half of it goes through, okay? And then half of the light just goes straight through this mirror, hits this mirror, comes back, right? And half of that goes back and hits the source, but some of it goes here and hits the eye. Now, what you need to know is that at this point, you are seeing light that has traveled superimposed on itself this distance and this distance, yeah? L1 and L2, okay? Two different lengths like that. And so what you have the potential for and what you do see is an interference pattern here, right? And if there is a half wavelength difference, this is very small, okay, between these two path lengths, and it's dark here, and if it's a full wavelength difference, right, an integer number, I don't know, I remember, I think you guys did this with Mr. Bossy last year, yeah? If it's an integer number of differences, then you see bright light. That's constructive interference. Do you remember this? Yeah. What you really see, by the way, is you put a screen here and you see concentric circles, right? Because, of course, the center of the screen is a slightly different distance than the edges or something like that, right? Because the screen is flat and all the points at the same distance are actually making an arc, yeah? So you see these concentric circles on there. Now, this thing is so fantastically sensitive that it detects half wavelength of light differences, minuscule differences, right? So if you walk up to the thing and you go, right? Yeah? You do the Nick Cage on it, right? Okay? The warm air from your breath changes the length of these paths, and the fringes go like this, right? In fact, the vibration of the floor and the heating cooling system of the building makes it go crazy. You have to put them on isolation tables, right? These things are so amazingly sensitive. If you touch one of the arms of it and start warming it up, the thermal expansion of the metal, which is just minuscule, you can see the fringes going whoa, 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 right? These are amazingly sensitive things. What you use them now, by the way, to do is to measure tiny, tiny changes of motion. So like you can set this mirror up on the wall, right? This could be like a foot-thick steel, and I press on the wall. And of course, Stephen, the foot-thick steel bends a little, doesn't it? Not much, but it has to bend a little. It's an elastic solid, right? And so you can actually measure the bending of what seems to be solid objects when you just push on it, yeah? It's like, whoa, 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 yeah? You can see these little fringes shift. So what they did was they set this thing up, and if you have, let's say we're in a medium and the light is traveling through that medium, it turns out that, let's say we're moving to the right, the path parallel to the motion, and the book does this enormous derivation of this whole thing, right, which isn't very exciting, but this path ends up taking a little bit longer than this path, right? Because this one's going full on into the stream and then going backwards like that, right? And then this one is across it, right? So there's a slight difference. This one would actually lag behind. The light from this path would lag behind the light from this path. And we ought to be able to see it, yeah? In fact, if we are, by the way, moving through the ether, all we do is we take this apparatus and we rotate it. We try to put it this way, then we rotate it 90 degrees, put it the other way, and you'll see fringes. If you are moving through ether and light travels through ether, you ought to be able to detect it. So they set this up, right? And in January, I mean, I have no idea when they did this, right? They rotate it. Yeah? Yeah? Do the fringes shift? No, that's because, by the way, ether doesn't exist. It's a flawed concept, right? They're trying to detect ether. Ether does not exist, right? And so they try this, they rotate it, January, nothing, right? So now either you have one of two possibilities, right? Ether does not exist, or in January, all the ether in the universe is traveling at the same speed, 19 miles a second that way. And we just happen to be at rest with respect to it, yeah? That's not what it could be, right? Right? Okay, so they try it again in June. They wait 6